Hi, my name is Emily Tracey. I'm in my third year of medical physics at the University of Windsor, and I'm here today to talk to you about pulse laser deposition of a silver film for laser-induced breakdown spectroscopy emission enhancement of bacteria. The University of Windsor sits on the traditional territory of the Three Fires Confederacy of First Nations, which includes the Ojibwe, the Odawa, and the Potawatomi. We respect the long-standing relationships with First Nations people in this place in the 100-mile Windsor-Essex Peninsula and the Straits of Detroit. A growing global concern is the antibiotic resistance crisis resulting from the increased use of broad-spectrum antibiotics. These drugs often need to be used because current methods of bacterial identification are relatively slow and can take 2 to 3 days. Our lab investigates the use of laser-induced breakdown spectroscopy, LIBS for short, to identify and classify the bacteria species because it can provide a much quicker diagnosis. The LIBS process takes less than a minute to complete. LIBS is a spectrochemical technique used to rapidly determine elemental composition. As shown in this illustration here on the right, a laser pulse is focused onto a target material, which absorbs the laser's energy and converts it into heat. This vaporizes atoms from the target. The vapor itself then begins to absorb the laser's energy to create a plasma. As the plasma cools, photons are emitted and collected by our spectrometer for analysis. This is what our experimental setup looks like. The white box in the top right over here is the laser. It is an ND-YAG laser operating at 1064 nanometers with a 10 nanosecond pulse duration and 10 hertz pulse frequency. This red line indicates where the laser would be. However, the laser is in the infrared region of the light spectrum, so it is not visible to the eye. On the left over here is our argon purge chamber with the sample inside. Our sample consists of bacteria deposited onto a nitrocellulose filter. This left photo over here shows the ablation event. Light from this ablation is fed into the blue optical fiber here to be collected by the black box, which is our Eschel spectrometer, and it creates a time-resolved spectrum. An example of a typical spectrum from the spectrometer is shown here. We see a relatively large carbon line, which comes mostly from the filter. The argon lines come from the argon environment that we shoot in. Phosphorus, magnesium, calcium, and sodium lines come from the bacteria. Different bacteria species have different ratios of these elements, which is what allows us to differentiate between them. We are looking to enhance our signal-to-noise ratio for 2 reasons. We want to detect smaller concentrations of bacteria, and we want to better discriminate between bacteria species. Work by our previous master's student proved that silver microparticles deposited on the filter underneath the bacteria enhance the LIBS emission spectra. Shown in blue is a typical spectrum for us, and in red is the bacteria spectrum that comes from bacteria on a silver filter. The red lines show a clear enhancement by a factor of about 4 to 5. You can also see silver lines, which are not a problem because they do not interfere with any of the bacteria lines. The silver increases the LIBS intensity because as a metal, it has many electrons to donate to the plasma, and it is a good conductor, which results in a more intense and hotter plasma. The main problem with the previous microparticle work was that the silver was not deposited uniformly across the filter, so each pulse showed a different amount of enhancement, leading to inconsistent intensity measurements. This graph here on the right shows silver intensity of 15 pulses shot on one filter, as shown in the illustration over here. The intensity begins at about 40,000 and decreases steadily after each pulse, resulting in intensity approximately 8 times lower after just 15 pulses. This indicates that the silver microparticles are being displaced after each pulse due to the plasma shock wave created by the ablation. Our proposed solution to these problems was pulse laser deposition of a thin film instead of microparticles. To perform pulse laser deposition, we focused a high-powered laser beam onto our silver target inside a 10 milliliter evacuated chamber. The silver target is vaporized in a plasma plume, which deposits the silver as a thin film onto the filter. This sequence of photos shows first a filter mounted onto our aluminum filter holder, then the filter holder being placed into the vacuum chamber, and here is the closed chamber. On the right, we see the inside of the chamber. The silver target consists of a thin silver foil wrapped around a copper rod, and this target is rotated continuously as the laser beam irradiates it. Preliminary experiments determined the optimal location of the filter in the chamber. We used a brass target because the brass rod shown here was readily available to us at the time. Different locations in the chamber gave varying amounts of brass coverage, as seen in the middle photo. Some locations gave a very visible gradient, such as this filter in the bottom of the image. Ultimately, we placed the filter on the side of the chamber toward where the lasers come from, as you can see in this top view of the chamber here. This allowed for optimum uniformity and easy accessibility for us to insert and remove the filter as well. We also used the brass rod to determine an estimate of deposition time to begin with. We started with arbitrary deposition times of 2 minutes, 4 minutes, and 8 minutes, and we found that the filters appeared much darker than those used in our previous silver microparticle experiments. We were concerned that this would be too much silver and it would cover the pores of the filter and prevent water from going through it during centrifugation. This led us to begin our silver experiments by investigating shorter deposition times of less than 1 minute. We created a filter that appeared very uniform to the eye, as shown here on the right, but we needed to investigate this uniformity more thoroughly using scanning electron microscopy and LIBS. First, we looked at the silver film using LIBS. As shown in the graph on the left, the average silver line intensity increases with deposition time as expected. The graph on the right shows the intensity of the individual pulses on one filter, and we can see that the intensity no longer decreases with subsequent shots as we saw before. This indicates that the silver sputters at a high enough velocity to be embedded into the filter and not be disturbed by the plasma shock wave. Using scanning electron microscopy, we found that the filter with a 40-second deposition time of silver, shown here on the left, showed no structural differences from a blank filter, shown here in the third photo. This indicates that we deposited a film that is extremely uniform and thin. This image here on the right was taken in between craters from laser pulses, and you can see that white specks of silver are visible. These are nanoparticles from the clusters produced during the LIBS ablation event. The SEM images of our film away from the craters, as shown over here, do not show any of these white specks, which is clear indication that our silver pulse laser deposition is a film and not individual particles. We observed no enhancement of bacteria spectra due to the silver deposition. This graph shows 6 different filters with various silver deposition times, each represented with a different color. Each filter has about 20 pulses that exhibit variation typical of all of our filters due to the stochastic nature of LIBS. Within each filter, you can see a linear relationship between bacteria lines and silver lines, as expected, because a pulse that gives a more intense plasma will cause every line to increase, silver and bacteria. What we had anticipated seeing was that the bacteria lines of a filter with more silver would be higher, but you can see that the average bacteria line intensity of each of these filters is approximately the same. All of these filters with silver also have lower bacteria lines in the filter with no silver, which is represented by the black squares. The reason for this is not yet known, but we have hypothesized that there may not be enough silver present to increase the temperature and the number of electrons in the plasma as anticipated, and instead the silver is actually attenuating the laser beam before its energy is absorbed by the filter. Our conclusions were that a uniform film was deposited as shown by SEM and LIBS. The silver film was also proven to not be disrupted by subsequent laser pulses, as the silver intensity showed no obvious decrease as each pulse occurred. We observed no bacterial enhancement regardless of deposition time. In the future, we plan to increase the amount of silver on the filter. This cannot be done indefinitely, however, as we are limited to a small enough amount of silver that the pores of the filter are not blocked. SEM showed promising evidence that the filter pores are not covered and water can still get through, so a larger amount of silver should be possible. We also plan to try a gold target instead of silver, as gold has even better thermal properties for our purpose that could provide more enhancement. I would like to thank my advisor, Dr. Stephen Raisey, my colleagues, Heike Ryan, Griffin Housen, and Emma Blanchette, and the sponsors of this project, an NSERC USRA grant, and the University of Windsor Outstanding Scholars Program. Thank you all for listening.